Professor Dr. Mahendra Panthi and Dr. Shruti Mishra. I take the honor to introduce both speakers. Dr. Mahendra Panthi Dr. Mahendra Panthi is associated with the University of Campinas, Brazil. He obtained PhD in mathematics from University in Rio de Janeiro. He is a gold medalist of TU for MSc in mathematics and also recipient of Third World Academy of Sciences Award for Developing World at 2006, conferred jointly by ICTP and RONAST. He has about 40 publications in international journals. Dr. Mahendra is involved in various academic activities such as review of PhD works, reviewer in journals, and research activities. His area of interest is mathematical analysis and modeling. I want to welcome Mahendra Panthi sir, and also I want to introduce Professor Dr. Shruti Mishra. She is senior member of technical team Sandia National Laboratories, Livermore, California. She develops and demonstrates integrated assessment framework to generate especially explicit information for energy environmental win-wins. She completed MS and PhD in applied economics from the Ohio State University. Dr. Shruti has been working on the domain of economic analysis for energy environment win-wins under changing climate regime as a Fulbright fellow and employee at the World Bank. United States Geological Survey and the United States Department of Energy National Laboratories such as Argonne and Sandia National Laboratories in California. The topic of Dr. Mahendra Panthi is some mathematical models in economics and environment. And the topic for Shruti Mishra is an integrated assessment framework for assessing the economic value of climate change impacts on hydropower plants. Now I request Dr. Panthi to give his presentation, and both of the speakers will get 20 minutes for their presentation, and the floor discussions and the question and answer session will be at the end of the both presentations. And I request all the participants to put their questions on the chat box. That will be easy for all to make the time management. So now over to Mahendra Panthi sir, please. Take the floor is yours.
Good morning. So thank you very much, Professor Suniti Hada, for introducing me. And also I would like to thank Dr. Saroj Gewale for this invitation, who approached me to be a speaker in this nice conference. Although I'm not much in the area of the conference, I will try to give some flavor in the subject. I am totally a pure mathematician, and I will do my best to give in the to address the public, which is much more general in this conference. So also I would like to thank the organizers who organized this international meeting in a very nice way. I have been watching, participating for the last 3 days. It is a very nice one, and thanks to the technology, I am long away from Brazil, and together with our Nepali friends and from other parts of the world. So I will introduce very basic model and just give you the idea how they have derived and how they can be used for the big, to address the big issues of, for example, some economy and some this global warming. So there are two models I am going to talk about. The first one, most of you already know, I hope. This is about the famous model in economics, and economics, most of you might have done. So this is the Cobb-Douglas production function. So in 1928, Charles Cobb and Paul Douglas published a study which they modeled the growth of the American economy during the period 1899 and 1922. The function they used, they proposed, is this PLK this PLK equal to BL alpha K power 1 minus alpha, where L is the total production, L is the amount of labor, and K is the capital invested. Here, B is a constant. I will explain you a little later. And alpha and 1 minus alpha is elasticity, and sometimes we write beta equal to 1 minus alpha is also the elasticity. So this model is used in many settings ranging from individual firms to global economics. So it has become known as the Cobb-Douglas production function. So this is not new to all of you here, I suppose. So how they have derived? Just a little idea. So in the beginning, they introduced it using the data from the American government. The data is organized in this way. So they took the they took the year 1899 is the baseline, and PL and K, production, labor, and capital, for 1989 is a base value, and they assign 100 for each. You can see over here. So for the subsequent years, they express the values just as the percentage of the base years. For example, they normalized it in some sense. They scaled it. So if 1899 was 100, then 1900 was 101, 112, like that. So based on this one, so percentage changes they used, and they make a table like this. And then they use the statistics idea, and they use this least square fit to have this equation over here. So this is the least square fit. So this is the approximate level. In fact, this is the good one, in fact. So what, and you already know, look at here, there is 3/4 and 1/4 is 1, is exactly here we have alpha plus 1 minus alpha is 1. So sometimes we write beta equal to 1 minus alpha. Okay. So my idea is how you can derive it using the differential equations without using the least square fit. So this is the first one I want to give you, and some consequences, some drawbacks, and some benefits, and some generalizations I will talk about. So it's a derivation of the Cobb-Douglas function using not the statistics least square fit, but the mathematical base. So P is a function of two variables, labor and capital. So it depends on two quantities, two variables. So the partial derivative, this one, partial derivative of this production, P, total production, with respect to K, provides the rate at which the production changes with respect to the amount of labor. Oh, sorry, this is not K. I made a mistake. This is L, dPdL. Derivative of this production with respect to the labor. So this is called the marginal productivity labor. Similarly, the partial derivative of the production with respect to K, this is the capital, this is the marginal productivity of the capital. So this is the two quantities introduced over here. So to find a mathematical model, you need some hypothesis, some hypothesis you need to make, or some assumptions. So there are three assumptions made by them. So either labor, if either labor or capital vanishes, then so the production, so will the production. So no labor or no capital, so no production will be there. The marginal productivity of the labor is proportional to the amount of the production per unit of labor. And the marginal productivity of the capital is proportional to the amount of production per unit capital. So these are the three hypotheses, three assumptions. So let us use these three assumptions. So the hypothesis 2 says the marginal productivity of labor is proportional to the amount of the production per unit of labor. It means per unit of labor is P over L, sorry, and this is the marginal productivity of the labor. So these are proportional. So these proportional means, so you have some constant alpha appears over there. So there, this marginal productivity of the labor is equal to alpha P over L. So what we do is, as we are doing this partial derivative, so we are making the second variable as a fixed. We are keeping this capital as a fixed amount. Like, so let us say this is a fixed amount. It means you are just solving the ordinary differential equations. So this is the separation of variables. So you are solving the ordinary differential equations, just you integrate both sides. So you are getting this expression. So logarithm, this is the logarithm of P equal to alpha times logarithm of L and some constant. So this we write as a logarithm just to make the expression easy. So if you organize this, so it becomes like this. So logarithm of P is this one. So it means you are keeping this capital fixed. So this production function keeping the capital fixed is given by this one. C1, this constant may depends on the capital. This is the fixed one. Okay, this one. So in the same way, the hypothesis 3 says the marginal productivity of the capital is proportional to the production per unit of capital. It means it's the same thing here. You are having P over K and derivative of P with respect to K, partial derivative. And again, you have this beta is the constant of proportionality you are getting over here. So now again, in this case, you are fixing the labor. Once you fix the labor, you are getting marginal productivity of the capital. Okay, then if you fix it, then you are as if you are doing for the single variable. It means you are solving ODE exactly as earlier. You separate the variables and you will get the production function giving like this. So here the constant may depend on the fixed labor that you consider earlier. Okay, now you have production function like this into fixing the capital, and here you have the fixing the labor. So if you are combine these two functions, then you are getting the production function like this. Okay, alpha and beta. But in the beginning, you remember this beta was alpha minus 1 minus alpha. It means alpha plus beta equal to 1. Then how come this? So here B is the constant that came out of C2L0 and C1 K0, but it is independent of L and K because we are fixing this in the beginning. Okay, so this should be independent of this. Now, from the first hypothesis, it says if either labor is missing or capital is missing, then there is no production. So it means this alpha should be bigger than 0 and beta should be bigger than 0. Otherwise, there is no production at all. So these are the first hypothesis like this. Okay, so let me first. So we have these functions. Then let us find the relation between alpha and beta that we did in the beginning. Okay, if one increases both labor and capital by a factor m, let us increase, then here you are increasing by a factor m, means ml and mk. So if you do this, then just you are doing here using in the formula ml alpha, mk beta, it means b m alpha plus beta. So this is the case you are getting here, and L alpha K beta. But observe that what happens here. If it is equal to 1, then you are having exactly M over here. It means, what does it mean? It means if you increase the labor or the capital by a factor of M, then you are changing, or you are getting the production also changed by a factor of M. If you increase, then it will also be increased by a factor of M. So this is why this is called the homogeneity property. So this is how Cobb and Douglas they use this alpha plus beta equal to 1. This is the reason behind that. Alpha is not 0, beta is not 0. This is equal to 1. So finally, this is the Cobb-Douglas function we have. So this is the analytical derivation. You use very simple partial derivative and just integration of the single variable, like, because you are fixing the second variable, then you are getting this equation. Okay, so then you have example, then you can maximize, you can minimize, you can do the optimization of this function, for example, in several ways. So how can you maximize the production, keeping some capital fixed, or the labor fixed, or changing the labor, changing the capital? So there are several issues you can address from here. You can compare with the other other companies or other industries like that. So this is an example. I think most of the Soros told me that here are many PhD scholars in environmental science or in the economics are involved are participating in the conference. Maybe this example might be interesting for them. I'm not going to do in detail, but if time permits, I will come back later. And anyway, I will share this slide. You can see it later on. So here, this is just the Cobb-Douglas production function, where X is the labor and Y is the capital, and this is given by this formula. So if the cost of the capital per unit is $5 and the labor is $6, and if your total amount you are investing is this much, input cost is 7,260, how can you maximize your production? It means how much X and how much Y you will be using to get the maximum production. So for this, you have to maximize this production function subject to this 5x plus 6y, where X is the labor and Y X is the labor. No, sorry, X is capital and Y is labor. So this might be 7,200. So what you do it, you maximize this subject to this constraint. So this is called this you do using the Lagrange multiplier, where it comes the this expression like gradient of P equal to lambda times gradient of G. So here just you have the gradient is given by this vector, and the gradient of G is given by this vector. If you compare and you use equation 6, just you are getting here X is 960 and Y is 400. It means just the one flavor you can use, you can maximize, you can use in your way. Okay, this is the one. So recall what are the things I told you in the beginning. So recall, this is the expression we got. Here, B is the factor of productivity. This is the the constant. It is, in fact, it is the ratio of aggregate output to the aggregate inputs. And alpha and beta are output elasticities of labor and capital respectively. It means percentage change of output divided by the percentage change of an input. So this, if alpha plus beta, so what we do in the Cobb-Douglas function is equal to 1. We are getting the constant returns scale. But it is not necessary that it can be generalized. Here alpha plus beta could be bigger than 1. It means increasing returns to the scale, and alpha plus beta could be less than 1, decreasing returns to the scale. So you can do in the beginning. It was like this. It is not always the case equal to 1, but it could be bigger or it could be less. Okay, so further consideration of this function is some merits, and there are some demerits too. So merits is this switch to the all nature of all. It switches to the nature of all industries, convenient in the international and inter-industry comparison, most commonly used function in the field of econometrics, and can be fitted in the time series analysis and the cross-section analysis, and can be generalized in the case of n factors of production. So this is not an easy job, but you can generalize it to the n factors of production. So far, we did only for the two, production and labor. And unknown parameters alpha and beta can easily be computed, because if you use the logarithm in the both sides, so this equation simply turns out to be a linear equation, and it is very easy to solve. So these are the sum of the merits, but there are demerits too. So it includes only two factors and neglects the other inputs. So if you use the original one, I'm talking about the original Cobb-Douglas function, and assumes the constant returns to scale, as in the last case I told you in the earlier slides, and considers only the quantity of capital available for the production. So it does not consider the other factors, influencing factors to increase the production like, and assumes the perfect competition in the factor market, which is unrealistic and based on the substitutability of the factors, and neglects the complementarity of the factors. So these are the limitations of this Cobb-Douglas production function. Even so, this is a very universal model and can be used in most of the economics and other problems too. So this is the first part. And the second part, what I am going to do is I want to explain global warming with a mathematical formula, a very simple one, also like this. So global warming is a topic on which opinions greatly vary. So there is no unanimity in the of the opinion. The Earth's climate is a very complex system. It involves the atmosphere, the oceans, the sun, vegetation, ice, and of course, human activity is also involved here. So how I think almost all we know that the Earth's surface gets heat from the solar radiation. This is the main source of the heat in the Earth's surface. So this solar radiation, it comes at the rate of 342 watts per meter square. It is coming one. So this comes here, and about 30% of this reflects directly from the reflected from the clouds, aerosol, atmospheric gases, and reflected from the surface of the Earth. And 168 about observed in the Earth's surface. And what happens that in the Earth's surface there is also the a generation of the heat, and it also goes away. So, for example, surface of the Earth radiates 390 watts per meter square, and it goes directly, about 40 goes directly to the radiation goes to the space. Some is observed in the atmosphere and come back as a radiation. So what happens is that there is no equilibrium. So there is no equilibrium. That is why we are experiencing the increase in the Earth's temperature. But how can we explain it in a very simple mathematical model? So in a simple mathematical model, to describe this phenomena is not an easy task, but I will give you the flavor. So the good one for this to explain is the energy balance method. What it says is that Earth is heated by the radiation from the sun, and that it has an average temperature of T. So let us try to find out how can you calculate the average temperature of the Earth. So T is the average temperature of the Earth. So some of this heat energy is absorbed when you get from the sun, and the rest is radiated back into the space. When we then reach to an equilibrium, when these two balance, when the getting radiation and the when the release of the heat from the Earth, if it were equal, then we are done. But it is not so. I will explain why a little bit. But in this model, we consider what we get and we release. Okay. So with this principle, what we do it, radiation in, how much radiation comes into the Earth. So heat energy or heat flux from the sun is given by R in, I say here radiation in is 1 minus A times S, where S is the incoming power from the sun. It is 342 watt per meter square on average. And A is the albedo albedo of the Earth. What does it mean? It means this is the measure, this quantity measures how much of this energy is reflected back. The current value of this albedo is 0.31. And here is a simple table. It says how this is the average one of the Earth. But in the surface, in the snow, this is, average albedo is 0.75 to 0.95. On ocean ice, 0.3 to 0.4. In desert, 0.24 to 0.3. In the grasslands, it is 0.1 to 0.2. In soil, 0.05 to 0.15. On the road, 0.5 to 0.1. And in the ocean, 0.07. So this is the average one like this. Okay. So this has a meaning a little bit later, I'll tell you. So what is the radiation out?
Dr. Panti, please,
Yes.
can you summarize this? Your time is running out.
Okay. So radiation out is given by like this, sigma eton. So sigma is the Stefan Boltzmann constant. T is measured in Kelvin, and E is the emissivity, and it measures how transparent the atmosphere is. So, for example, in the moon, there is no atmosphere, almost no atmosphere, so E is 1. In the Earth, it is 0.61. So, what the temperature of the Earth? So, in the equilibrium, it means in the energy balance, the radiation in and radiation out are equal. It means these two quantities are equal that we derived earlier. From here, if you manipulate, T is like this. Okay, so here are two factors. So here S is fixed, this sigma is fixed. So A and E are different. So these are not fixed quantity. So if you use at the average, I told you earlier, these are the cases. So average temperature of the Earth you can find is 15 degrees Celsius. Just give you the idea. So here, this is the formula. As I told you, this is not fixed and this is not fixed. Look at here. If A increases, for example, if A is bigger, then this quantity is smaller, means temperature is smaller. If A is smaller, then 1 minus A is bigger, it means temperature is bigger. But what was A? So A was the albedo number. Okay, albedo of the Earth. This albedo of the Earth, if this decreases, means this one increases, it means temperature increases. Look at here, on the snow, this is the higher number. On the road, on the soil and the ocean, it is less number. So if the ice is melting, then you are not reflecting. It means your temperature is increased. And in the other way, emissivity, if the emissivity decreases, if it is less than 1, it means if your atmosphere is not transparent, if it is polluted, like if there is greenhouse gases, it is polluted by greenhouse gases, it means it is not reflected by. So there is emissivity decreases. Emissivity decreases means you are dividing by a number less than 1, means your temperature increases. So greenhouse gases are the main factor, to decrease the emissivity, and this emissivity decrease in emissivity implies the global warming, like temperature of the Earth increases. So this is a very simple model, but you cannot explain it in a full model, just to have an idea. But the big climate models are, this is in the big form where it considers all the factors as we showed in the beginning. So I think there is no time much. I will stop here. So thank you very much for your attention.
Thank you, Dr. Mahendra Panti sir. It was really interesting to see how we can model the real life situations like in global warming and the climate changes mathematically. It was very nice. Thank you very much, Dr. Panti sir. There is already some questions on the chat box. We will take that at the end of the presentation of Dr. Shruti also. So Dr. Shruti, can we have your presentation, please? Yes.
Let me look it.
Shruti, your audio, yeah, you put on your audio. Yes, yes, good. Okay.
Okay, fine now. All right. Can you see my slides?
Yes, yes, ma'am.
And can you hear me?
Yes, yes, ma'am.
All right. Yeah.
Can you
Good
please
morning,
put the
everybody.
slide in full form?
Better?
Yes, yes, yeah. Very nice.
Oh, I'm sorry. For some reason, this screen is a little bit. Okay, let me see. Okay. Why is this? Yeah, is this better?
Yes, yes, yes. It has gone more on left side. You can make it in center or something.
Yeah, it might be my problem here. I don't know how to fix that.
It's okay, man. You can start. Yeah.
All right.
Yes.
Yeah, when I do this, it just.
No, you do it. So whatever is comfortable to you. Fine, fine, man.
Yeah, I don't want to just lose my time here. Is this better? Is this
Yes.
better, or I should go for full screen?
No, okay, fine. Whichever is comfortable.
All right. Okay. Yeah. Good morning, everybody. Thank you so much, Dr. Suniti Shrestha, for your kind introduction. And thank you, Dr. Govita Tamang, for inviting me to share this. And I also thank the whole organizing team for providing me this opportunity to share some of my work. So Dr. Ponti's presentation set up the stage very well for my presentation. So the equations he used were used in my work that I'm going to share with you. In the last 3 days of this conference, scientists and experts from academia and industry and regulatory agencies have highlighted on various aspects of sustainable energy for climate change, mitigation, and adaptation. So today I am going to share this integrated assessment of energy sector to support climate change mitigation and adaptation. I will share with you some research projects and programs in this domain of energy sector and climate change that I worked with different scientists from multiple disciplines while working at different organizations like US Geological Survey, World Bank, and two national laboratories under the US Department of Energy, Argonne and Sandia National Lab. So this is the broader integrated assessment framework that I use for my analysis. So this integrated assessment framework couples biophysical models and economic analysis models, right? And this, in the biophysical modeling component, we have this energy system and the environmental system, and we model the interaction between these two systems. And the output of this biophysical model goes into the production function, just like Dr. Ponti showed that Cobb-Douglas function. So similar kind of production function depending on which energy sector, solar or wind or coal or what have you, and also the different kind of environmental factors, right? So based on that, we have this production function, and then on that production function, we also include different kind of ecosystem services, including the value of climate change mitigation or the social cost of carbon, which is a metric of global climate change impact, right? And then we generate information on costs or benefits or risks or incentives for different kind of sustainable energy technologies, right? And that kind of sustainable energy technology gets us into this environmental win-win situation, in an energy and environmental win-win situation, right? So we have applied this integrated assessment framework for different kind of energy issues and energy and climate change interface issues, such as, in terms of like climate change mitigation. We have worked on social cost of electricity generation from coal. And in case of adaptation, we have looked at how climate change can impact hydropower plants, and in terms of climate change mitigation and sustainable energy. Again, we have looked at the solar energy as well as the bioenergy and biofuel production. And we have got some publications out of this work. And if anybody is interested, I can share those publications with Dr. Govinda Tamang, and you guys can have access to that. Many of these publications are already available online as well. So today I would like to focus mostly on the climate change impact on High Mountain Asia region. We recently conducted some work that was funded by NASA, and a big team of scientists from different organizations, including Kathmandu University. We worked together on this. So High Mountain Asia is particularly vulnerable to these changes in climate. The region has extensive snow and glacier cover that is responsible for regulating downstream water supply. And any changes in snow and glaciers, such as Dr. Ponti just explained, like albedo effect and increase in temperature, so that impacts the snow melt timing and glacier dynamics, and that has impacts downstream on water availability, and that translates to food, energy, and water, food, and energy security nexus, right? So such changes in hydrology in High Mountain Asia may impact up to 2 billion people downstream, because it affects agriculture, different kind of ecosystems, industry, transportation, energy sector, fisheries, and recreation. So as a result, the whole social, environmental, and economic fabric of High Mountain Asia region gets affected. And in terms of sustainability of this highly interconnected food, energy, and water nexus will be a fundamental and increasing challenge in this changing climate regime. So if we look at if we want to look at the climate change impacts on water availability and its downstream impact, we need to first look at what are the sources of High Mountain Asia rivers, right? What are the water sources? They can be categorized as glaciers and snowmelt, water from precipitation, rainfall, water from surface water, different kind of lakes, and groundwater flow. And climate change impacts on all these factors differently. And also the impact of climate change on these factors varies spatially from at different locations, right? And so the timing and magnitude of runoff in rivers depends on this hydroclimatic interaction, and it varies especially from basin to basin. So what I'm trying to show here in this figure is this big High Mountain Asia region and all these small sub-basins. And in each subbasin, if you look at it, this blue area is glaciers, glaciarized areas, and the area like the area under glaciarized, like the share of glaciarized area in each of these subbasin varies. And the sources of water for each of these subbasin varies depending on how much snow it receives, how much rainfall it receives, and how much is the other sources, right? The surface water and groundwater. So in addition to that hydrological aspect, another important aspect of climate change impact on food, energy, water nexus is also the water demand, right? And water demand depends on what kind of economic activities are there in each of these subbasins, whether it is heavily focused on agriculture, whether it is focused on hydropower generation, and what kind of mix, what kind of intra-sectoral water allocation is required, and things of that nature. Also, the other factor that determines the climate change impact is the risk mitigation capacity of downstream population in the region. So when we talk about different kind of economic activities and ecosystem services that the high mountain Asia rivers support, we talked about hydropower generation, different kind of recreational benefits like rafting and things like that, the fish and wildlife, as well as if we go further down, there is this drinking water supply, irrigation water supply, and others. So the spatial variability in water supply and demand, it varies from east to west as well as north to south. If we look at the high altitude region, it has a lot of headwater for holy rivers and snow and glaciarized mountain that support certain kind of activities. Similarly, in the foothills of Himalayan region, the nature of economic activities are a little different. And as we go further down, we focus more on irrigation, irrigated commercial farming, fisheries, and several industries. So now I would like to focus on the case study that we completed. And because as I tried to emphasize earlier, the impacts varies from subbasin to subbasin, and I would like to reinforce this throughout my presentation that we need to look at hydroclimatic dynamics in subbasin scale, and also look at the different infrastructure and economic activities at subbasin scale, so that we get prepared, we can generate this scientific information to manage those water sustainably, so that the impacts can be mitigated, the climate change impacts can be mitigated, right? So we looked at this Naltar hydropower plant, and we looked at the Trishuli hydropower plant, and we looked at two different locations, one in Karakoram region and one in Central Himalaya region, because the hydroclimatic dynamics are completely different in these two regions. However, the kind of hydropower plants we looked at are very similar to each other. They have very similar characteristics. So the earlier integrated assessment framework that I shared with you, we modified a little bit to show what kind of work went into in assessing the economic impact of climate change on hydropower. So we have these climate models. We used 16 scenarios based on 8 global circulation models and 2 emission scenarios, regional concentration pathways, 4.5 and 8.5. And we looked at the change in hydrology using this water balance model that takes into account snowpack and glaciers all the way to the groundwater, and it provides the hydrologic flow under different scenarios, different climate change scenarios. The output from this water balance model goes to this hydropower model to quantify the change in electricity generation in Naltar power plant and Trishuli power plant under 16 different climate scenarios, and that goes into this economic analysis model to estimate the economic impacts. So here you can see these graphs. These are the simulated river discharge. So I'm taking you from this framework, right? And there are a number of models and equations that went into this work. If you guys are interested in it, you can look at our papers, right? And maybe I will also be able to explain some of those during the question answer session. But for the broader audience, I thought maybe I should just show you some results, and we can go into details as you guys are interested in it, okay? So in these figures, we have this annual discharge for Naltar, and this one is for the Trishuli, and this one is for Naltar. And this one here is the summer discharge, and we see the variability in discharge under different scenarios, right? The blue lines are for regional consultation pathway 4.5, and the red one is under more climate change impact indicating scenario, that is RCP 8.5. And what we see is in most of the GCM RCP combinations, we looked at 16 combinations, and the summer discharge tend to increase by about 10% for at the mid-century, right, by 2050. And then we look at the sharper decline, and at the Karakoram site, we see more decline than at the Trishuli site, as you can see here, right? In Naltar, you see a sharp decline than here. We also wanted to look at, different kind of source water analysis, because depending on how much of the water comes from glacial melt, how much of it comes from snow melt, and how much comes from the precipitation, the mitigation measures downstreams are different. And these two figure shows the average monthly snow and glacial melt fraction discharge in Trishuli and Naltar. So these are solid lines that you can see. This is for the glacier, this glacial melt, and this is for the snow melt. And what we found is in most of these global circulation model and regional concentration pathways combination, 16 climate change scenarios, the summer discharge initially tend to increase, and then I'm sorry. So this one is for the monthly distribution, right? So if we look at the summertime, some of the snow melt and glacial melt fraction, so here we have like glacial melt and snow melt, and we haven't shown the composition of the rainwater here. The source of water during the spring month so here the spring month is dominated significantly by snow melt under 8.5 RCP 8.0 scenario as compared to RCP 4.5. So on the different timing of snow melt and glacial melt and how their contribution changes, you can see from these two graphs for these two areas. That went into this hydropower economic analysis, And here we have shown the hydropower generation, how it changes over the period until 2100. And we got the data for this Naltar power plant and Trishuli power plant from these power plant operators. And then, of course, we went through the proper channel, and we received those information to conduct this research. And we see that the largest differences in generation between RCP 4.5 and RCP 8.5 scenarios. So these are all the combination of different climate change scenarios, the global circulation model and emission scenarios, 4.5 and 8.5 scenarios. And the average estimated values for under these both 4.5 and 8.5 emission scenarios are higher in the month of February, March, April, and then October, November, and December for Naltar. And for Naltar power plant, we found a higher interannual variation in revenues. And in April, because of this increased snow melt, the profit under the RCP 8.5, like high emission scenario, was to double than that under RCP 4.5 scenarios. However, in the month of May, the expected loss, we estimated expected loss under both the RCP scenarios. And in terms of Trishuli, February, March, and April, the power company will keep incurring losses. And we also looked at what happens in the pre-peak water decade. That means before the glacier melts, and then also in the peak water decade, wherein the glacier melt is the highest. And we also found that there is no significant change in rest of the months than February, March, April for Trishuli, because most the share of water comes from precipitation, and we receive monsoon rain that takes care of those losses.
Madam, will you manage the time, please? Okay.
Yeah, so this is the summary. So basically, we have based on the quantity of glacier and snow melt area, and how much of the share of river flow comes from rainfall, and how much from surface water and groundwater. It varies from subbasin to subbasin, and it is important that we look at subbasin scale analysis, right? And the timing and magnitude of runoff depends on these different kind of sources, which varies with climate and geographic location. So each, also we need to consider, like in different subbasin, we have different sets of crop, different sets of cropland area, livestock population, and different kind of infrastructure, hydropower, irrigation, and also the human population. And we need to take care, we need to take into account both the climate-hydrology as well as these human aspects and the infrastructure aspects in order to quantify, or in order to assess the climate change impacts on energy sector and other important sectors in the region. We stored how we can use these multiple disciplines to estimate the economic values of climate change impacts on energy sector as well as food and other sectors. We have those details in the papers that I mentioned earlier, if you guys are interested. We also looked at the impact on hydropower and fisheries in one of those papers. And this kind of work requires a team of multiple disciplinary scientists, right? I also showed you how we can use this integrated assessment framework, and the scientific information we generate from this kind of framework would be helpful for informing various water, food, energy security decisions. And with acknowledgement to all my collaborators and funding agencies, I would like to end my call. Thank you for your attention.
Thank you. Thank you, Shruti Madam, for your nice presentation and sharing the findings of your research. It was really, really very informative and very interesting. Thank you very much. Now I will call the questions from the floor. I think there are some questions on the chat box for Dr. Panthi also and for Shruti Madam also. So I will first, you can take some questions from chat box, Panthi sir. And actually
Yes.
this Cobb-Douglas function, this was the model that I used in my thesis of MSc statistics also. Yeah.
Very nice.
Okay.
So it was recalling you.
Oh yeah, yeah. And I think it was very interesting and applicable, but I think there are so many models coming nowadays and people go
Yes.
for the new models.
Yes.
I think it's your experience also. Okay, Panthi sir, this question from Shruti. Yeah.
So
How
there is a
about the
question.
data analysis? Yeah.
Yes, I think we can use this panel data analysis, but I'm not. I have not worked on it. As I told you, I'm basically focused on what's in the theory part of the science, what's physical models than the economics. But I think it is possible to use it. And another question is here. Sri Ram Kandil asked. Nice to know how we can apply in the research. Actually, as you have saying, this is just a model having a limited scope. No, what I told you that this is the energy balance just as a prototype to check how can you calculate the average temperature and what is the tendency, what are the factors affecting the global temperature. This is the case, but in the to find out the real scenario, this is not enough. You have to generalize it, where the temperature depends on the time. So there are several other things. There was no time, so I could not tell. But this is just to have an idea. But there are generalization of the this energy balance model that I told you today. And the last question I saw that is about the Cobb-Douglas functions. They say only the two. There are you can generalize it for the several inputs also. There is a generalization. I told you this is the original Cobb-Douglas functions only with two variables, labor and the capital. But you can generalize it to the n variables and any finite variables. There are several other works, several generalizations you can do it. And here I only just give the flavor of the model. I
want to add here one thing.
Yes.
In 1980s, I think in 1980s, the Nepal Rashtra Bank has used this Cobb-Douglas function in agricultural sector, taking about 15, 16 input variables. So you can check those literature in 1980s.
Yes. Yes.
Yeah. Panthi sir, you have to say something, otherwise we go to the Shruti madam.
Okay, I have that. That's all. Thank you very much.
Shruti madam, you have one question from Navraj Patel.
Thank you for your question, Navraj sir. Yeah, scientists scientists have found that snow. First of all, let me tell you my story. Okay, I started like same way like you did. It is only glaciers. Glaciers are retreating and everything is getting impacted downstream. However, glacier dynamics is completely different than snow. And then when we look at the climate change impacts, those are not only the things that we need to look at. We need to look at how much of the river flow is coming from snow and glacier, and how much of it is coming from precipitation, right? Of course, snow and the glacier dynamics matters, and what time snow falls, how much, what is the thickness of the snow that is falling, and when it is melting, that is very important. And in case of Trishuli Basin, if we go upstream near Langtang, the share of glacier and snow melt water is up to 40%. So if you have something up there, then the impact of climate change on hydropower, or if you have irrigation by chance, those will be impacted. But if you go further down, the Trishuli power plant we looked at, it was further down, and the share of snow and glacier matters only in the month of March and April. And rest of the time, the precipitation, monsoon water is so much more that they have extra water to take care of. So that is the situation in Trishuli Basin. And if you, thank you for requesting for my paper. Please contact Govinda sir, you might have his contact, and then I can send those papers to you. You can also find them online. If you Google them, you can find them, but I would be happy to email you and even like talk to you if you are interested in doing similar kind of work in Kaligandaki Basin.
Thank you, thank you. There is one more question for Dr. Pandey. Would you like to take that, or what do you say? How do you find mathematics connected with global warming? Well, actually, yeah. I think this is appreciation. Yeah, not a question.
Yeah, this is just thank you very much. This is a very good, nice compliment. Yeah.
Thank you very much, sir. And again, I think we should take one snap. So I request everybody to come in the video. Please. Vijay sir is taking picture. Everybody can. Okay. Thank you very much. Thank you very much for this session. It was really interesting. And thank all the participants also for your participation. Thank you very much. And now I think this plenary session is completed and it is closed here. Now I request all the participants to go to the another parallel sessions. Thank you very much. Thank you, madam. Thank you, Pandey sir.
Thank you.
Thank you. Bye-bye now.
Bye-bye.